You are given a binary string that contains zeros and ones. Let us consider the prefix sum array, and any entry of the prefix sum array is nothing but the sum of all of these integers written down over here. So you can see that the sum of all of these integers is 3. We have written 3 over here. Then from this prefix sum array, let's figure out the modulo of each integer in the prefix sum array when you divide it by 2. Basically, you convert this prefix sum array into prefix sum array modulo 2. So you can see that all the odd numbers get a 1 corresponding to it, and all the even numbers get a 0 corresponding to it. Now this array that you have just created, this is also a binary string, just like the original binary string that was given to you. But now we say that you are not given the original binary string or the original prefix sum array modulo 2, but you are given some modifications of it. That is, I have taken this array and I have randomly flipped some bits. So I might have made this a 0, I might have made this a 0, I might have made this a 0, might have made this a 1, etc. So you can see that I might have done a lot of flips in both the array, in the original array as well as the prefix sum array modulo 2. So I have picked this element and flipped it, picked this element and flipped it. Now once I do this, then the array that is given to you, you will realize that this prefix sum array is not really a prefix sum modulo 2 of this array anymore, because you have done random flips. So you have to figure out what is the minimum number of flips to go back to the old state, that is, go back to a consistent state. And what do I mean by a consistent state? A consistent state is the one wherein after a series of flip, the array A that you have achieved and the P array that you have achieved, this P array should be a prefix sum modulo 2 of this binary string that you have achieved. So how do you figure out the minimum number of steps to reverse the set of flips that I have done? Of course, one possible solution is to flip everything to 0, because if you can create 0 0 0 in A and also 0 0 zeros in B, this is a consistent state, but this will require how much cost? This will require cost equal to all the number of ones that you have in the lower array as well as the upper array. So that is just one possibility. I want you to find the minimum number of flips that you have to do to achieve a consistent state. So take a minute to pause this video and try out the problem for yourself. And this is not a difficult problem at all. It's just a basic, very simple dynamic programming problem on binary strings. And I'm just creating this video for people who are new to dynamic programming or new to dynamic programming on binary strings. So how do we solve this problem? So instead of jumping to the solution first, let us first explore the properties of this prefix sum modulo 2 and how we can use some existing tools to simplify things. Now you can see that you can construct this prefix sum array by two methods. One is you construct the prefix sum, this entire thing, wherein you have 3, you have 4, you have 5 and whatnot. But you can also construct this prefix sum array modulo 2 without even constructing this middle array. And how is that? Because of this interesting property that A plus B plus C modulo 2 is nothing but A modulo 2 plus B modulo 2 plus C modulo 2 and entire modulo 2. That is, instead of accumulating the entire sum and then dividing by 2 at the end, you can instead keep on accumulating the sum and then immediately doing modulo 2 at every stage, no matter how much you want. Like you can do modulo 2 at each stage. So in fact, you can see that 1 is written over here and then you encounter a 0. So 1 plus 0 is 1. So you write 1 over here. Then 1 plus 0 plus 1 is 0, right? So you write a 0 over here. So this means that this prefix of I is nothing but prefix of I minus 1 plus a of I, and here you are just doing modulo 2. So, and of course, since we are dealing with binary arrays, then this a of I will be in 0 to 1. And like I said, that every time you take modulo 2, so this will also be a binary array in 0 to 1. So you notice some interesting property over here, that in the modulo 2 space, basically the Z2 space, you are adding two integers. So what does adding two integers mean? So if you are familiar with XOR, you will realize that addition in Z2 is same as XOR. So XOR is nothing but binary addition. So because if you think about it, 0 plus 0 is 0, but 0 XOR 0 is also equal to 0. 1 plus 1 is 0. Why? Because 1 plus 1 is 2, and then 2 modulo 2 is 0. So 1 plus 1 is 0, but 1 XOR 1 is also 0. 0 plus 1 is 1, but 0 XOR 1 is also equal to 1. So in fact, XOR is nothing but binary addition in modulo 2. So you can view this entire problem from a different angle. That is, given this array, this lower array, which is the prefix sum array modulo 2, this is nothing but the prefix XOR array. Not that it helps us solve the problem or anything, but this will definitely help us simplify the problem and reduce a lot of casework. Because now you don't have to worry about modulo 2 anymore. Entire modulo business is gone. You just have to deal with prefix XOR. So now the reduced problem becomes that you are given two arrays A as well as the prefix XOR of A, and some of the bits might be flipped in A as well as the prefix XOR of A. So you have to figure out how much more bit flips that you need to do, such that this lower array, which is P, and the upper array, which is A, this should become the prefix XOR array of the upper array after doing the series of flips. Right? Now, how do you solve this? So in these kind of problems, let's start with the simplest case first. That is, instead of trying to correct the state of the entire array, let's pick the last element of the array and see what states can it possibly be in. So consider the last element, and of course you have to consider them in pair, because AI and prefix XOR of AI, they will behave in a certain fashion, right? They cannot behave independently. So what all states can it be in? So you can see that the original entry at the top might be 0 or 1, and then the prefix XOR can also independently be 0 or 1. So it can either exist in this state 0 comma 0, or in this state 0 comma 1, or in this state 1 comma 0, or this state 1 comma 1. But are these four positions actually feasible? Because sure, the upper array can freely vary between 0 and 1, but are these all these states actually feasible? Like, is it actually possible to have all four kind of different states for this upper and the lower element of the last part? So to do that, to figure that out, let's notice that if we had the original array without any bits flipped, and you have already constructed the lower array, which is the prefix XOR array, then as soon as you selected one element over here, then this element was already predetermined. Why? Because if this is the prefix XOR, then this element will be prefix XOR of this, basically the last element over here, and then XORed with this will appear over here. Therefore, all of these four positions are not possible to achieve here. It will all depend upon what is the array that you have constructed so far, and what is the last prefix XOR that you have stored, because this is the only thing that matters. What you have stored over here doesn't matter. Whatever you have stored over here, that encodes all the information. So if you have encoded a 0 over here, then that would mean that if the prefix XOR of this entire segment is 0, then if you are placing a 0 over here, you cannot place a 1 over here, because the prefix XOR of this entire segment will be 0 only. So you have to place 0 with 0, or if you want to place 1, you have to place 1 with 1. So this means that whatever construction that you have done so far, so suppose you have this array and you have this array, to identify what possible states the last element can be in, you only have to remember what is the prefix XOR that you have computed so far. You don't have to remember what did you place here, 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 and so on. So if you define your DP definition something like DP of I j is the minimum bit flips to make the first I elements consistent. I elements consistent such that the prefix XOR of the first I elements is equal to j. Basically this j parameter is nothing but this lower entry that you see. Now of course this parameter can be up till n, because there are total of n elements, but prefix XOR can only be between 0 and 1. So the DP table will only be of n cross 2. Now this old XOR that you have computed, so this old XOR, which is that green box that you see over here, this old XOR, this can only be in this set 0 and 1. So let us fix this set and assume that this old XOR is either equal to 0 or it is equal to 1. Then after this, you have a free choice to place any elements that you want over here. So if you want to place something in the first array, you can do that. So this placement, that can also freely vary, because nobody is restricting you to place a 0 or a 1 over here. But the lower part, this lower part will be predetermined. Once you have taken this, once you have fixed this old XOR and you have placed something over there, this part will be predetermined. So then this new XOR would become nothing but this old XOR that you have computed, and you are XORing with this element that you just placed. So this means that if you add this after this, you will create a DP state that has I elements and ends with this new XOR. So this way you can get the transition. Now to get the transition, you have to figure out the cost to achieve this. What is the cost to place this 0 or the cost to place this 1? Now if a 0 already exists at this position, then the cost to place a 0 is 0, but the cost to place a 1 is equal to 1. So even now you can see a fancy trick of XOR that for 0 and 0 the answer is 0, the cost is 0, but from switching from 0 to 1 or vice versa, the cost is 1. This means that the cost of switching from x to y, so the cost of switching from x to y is nothing but x XOR y. Even here you can see that if you use XOR, your code will become much simpler. And why is this true? Because if x is equal to y, then the cost should be 0, and yes, x XOR x is equal to 0. But if x is not equal to y, it means that you have to flip that bit, then the cost will be equal to 1. So if x not equal to y, x XOR is equal, x XOR y will be definitely equal to 1. Right? So this means that this time your cost, you can place either a 0 or 1, and then your cost will be the upper cost to the cost to flip this bit and the cost to flip this bit. So it will be a of I, which is the existing element, and you XOR it with whatever you want to place, right? Plus the cost of the lower element, which is nothing but b of I, or the prefix XOR of I. XOR it with what do you want to achieve over there. You want to achieve this value, so you XOR it with this new XOR. And so what does this dp value represents? Dp of I comma new XOR, it means what is the minimum cost to correct the first I element such that the last prefix XOR is equal to this. So what is the minimum cost? The minimum cost is nothing but the cost to correct the last element plus the cost to make the last prefix XOR as this. So in this manner, you can have O of 1 transitions, and the overall time complexity of the algorithm will be O of n. So let's look at the code, and hopefully this will simplify things. So you have defined dp of ij as the minimum bit flips required to fix the first I element such that the last prefix XOR, or basically the last element in the lower array, which is nothing but the prefix XOR, is equal to j. Then this is the base case, like for the first element, if it is 0, then the prefix XOR will also have to be 0. So that's why you determine the cost as by doing it 0. Or if it is 1, then prefix XOR will also have to be 1. So you determine the cost by doing the XOR with 1. And then you iterate from left to right, and then you make a choice that for the array that you have constructed so far from here to here, what is the final XOR that you have created. So this final XOR that you have created up till elements I minus 1, this can be either in 0 to 1, and then you can freely place one element over here. It can either be 0 or 1. Once you place that element, the new XOR will be equal to the old XOR XORed with the element that you just placed, and this will be the cost to place the upper element and the cost to place the lower element. And once you have placed the lower element, this new XOR that you got, this is just one state of the dp. So you can update that dp of I comma new XOR is nothing but the old cost plus this new cost. And finally, at the end, you actually do not have any restrictions on which configuration the last element should be in. Like should the final prefix, or should it be 0 or should it be 1? There is no restriction. So that's why you take the minimum value out of it. And this way you are able to solve the problem in O of n using some tricks from the XOR world. So these XOR tricks, they are not actually needed to solve this problem. You can still solve it by just doing case analysis with modulo 2 and whatnot. But yeah, this is just a fancy way to simplify things. And more than that, like this is just one of the most basic dynamic programming problems, I would say. So maybe take your time to understand what is going on behind the scenes, because I cannot dive deep into all of these dp parameters, etc. for easy dp problems. So I am still creating this video so that you can at least take this problem, analyze it by yourself, and then see whether these dp definitions make sense or not.